name is Miqhail.
Hi, my name is Amirun.
Hi, my name is Sufi.
And we are from Group 5.
Now I am going to talk about the reaction engineering part. For the type of the reactor and catalyst used, based on our research, we have chosen the trickle bed reactor because it is a multi-phase reactor. Next, it can conserve energy because it has low energy dissipation rate. Next, it has high catalyst loading per unit volume of the liquid, which makes it superior when compared to other slurry reactor. In addition, amount of impurities in the KTA is too high for the polymerization. And lastly, the trickle bed reactor is widely used in hydrotreating processes in petrochemical industries, petroleum refineries, and chemical industries. Okay, next, for the catalyst use, we have chosen the palladium SN catalyst on the functionalized multi-wall carbon nanotubes. So, why we choose this catalyst? Because it has lower CTA hydrogenation activity due to alloy formation and palladium surface blocking due to SN addition. The SN addition led to decrease in the decarbonylation rate of 4-CBA, thus enhancing the product selectivity. Okay, next, it has positive effect on selectivity by increasing the rate constant ratio of the hydrogenation rate. And the last one is sufficient to decrease the 4-CBA content of CTA from 2100 ppm to 5 ppm without excessive hydrogenation.
For my part, I'm going to explain about the description on how the chosen reactor separator system works for the dehydrogenation of TA, crude TA to purified TA. Okay, firstly, purified TA is produced through two separate sections, which is crude TA and purified TA. The crude TA is commonly produced by homogeneous liquid phase p-xylene oxidation at 200 degrees Celsius and 1 atm. For the purification section, crude TA is dissolved in water at 270 degrees Celsius to 290 degrees Celsius at 1 atm. During the feed preparation section, crude TA powder enters into slurry feed drum and mixed with mother liquor. Heat exchangers step up temperature at 285 degrees Celsius using steam coming from crystallizers. Next separation process, the slurry is inserted into some centrifuges which separate TA cake from solvent. It is then mixed with water and pumped to rotary vacuum filter. Wet purified TA cake goes to dryer at low pressure to remove the humidity. And lastly, the dried purified TA powder transferred to purified TA, checking silos through powder conveying system for fine.
For the third part, I'm going to talk about the strategy to maximize the selectivity and yield of purified TA and to minimize the side reaction. So the selectivity means the ratio of desired product to undesired products, and yield means the ratio of desired products to the products that will be formed if the conversion rate of the limiting reactant is 100%. So we have 6 strategies to maximize the selectivity and yield. So for the first one, we use optimum temperature. We purify our TA in subcritical water, which is higher than 25 degrees Celsius. We use 523 K, which is optimum temperature for the purified TA. When the temperature is higher, the solubility will increase based on what Takabayashi research. So there will be more reactants dissolved in the water when the solubility increase, which will also increase the products and the yield. And for the second step, we increase the cobalt and manganese ratio. We will increase it with relative to bromine. So our selectivity of purified TA is also same as the selectivity of paraxylene oxidation. When we increase the cobalt and manganese ratio, the activity of catalyst will also increase. So with this increase in the activity, the rate of oxidation will become optimum, which is the desired condition for our maximization of yield and products. The third one is the position of equilibrium to the right. When the position of equilibrium lies to the right, the concentration of products will be higher than the reactants, which is our desired condition. So we increase the concentration of the solute, then the position of the equilibrium will lie to the right and the products will increase. The fourth is increased catalyst loading. We will increase the palladium loading, which will provide greater activity and performance. When we use 0.5 weight percentage of palladium in the catalyst, we can remove 99% of 4-CBA with a minimum amount of side reaction. The fifth one, minimize side reaction. When we want to increase the yield and selectivity, we will try to minimize the side reaction. So by doing this, we can reduce the undesired products form, and we will have the more percentage of the desired products form. For the sixth one, we use PDFN over FMWCMP catalyst. This type of catalyst can decrease the decarbonylation of 4-CBA, and this will increase the product selectivity. For the next one, I will talk about how to minimize our side reaction. As we all know, side reaction is actually unfavorable for our reactions. So when we produce side reaction, it will use up our reactants, and this will waste our cost and decrease the effectiveness for industrial purpose. So for the TA purification, we will try to decrease the decarbonylation process, which is side reaction. So we can decrease the concentration of oxygen, because when we have more oxygen, there will be more decarbonylation process, which we don't want based on Zhou 2006.
Next, I will talk about the sizing of the reactor. So this is our calculation for the sizing of the reactor to produce the purified TA. So as you can see, this is our equation. Then our assumption, we assume the reaction is steady state and is first order based on the equation. And so the reaction will only depends on the concentration of 4-CBA. And the reaction will be in liquid phase, so there will be no volume expansion. And they don't have no pressure drop in the system. So this is our calculation. First we get the 30,000 from the question, and we convert it to the mole per year, because the Ca is in mole per volume, so we have to convert it to mole per year. And in here we already convert our mole per year to mole per hour. So we do our volumetric flow rate, we calculate it based on this formula, and we get this. So step 3, we will calculate the rate constant. We get the K value from the Journal of Manly. So I will get it. This is based on 1,200 RPM. Then we get 900 0.7. So this is our formula used to calculate the weight of catalyst. Actually, it's the sizing of reactor. So yeah. You subtract the K value and the volumetric flow rate value into the formula, you will get 4.63 meter cube per hour for our reactor.
Now we move on to separation process 2 part. For the type of separation system used to produce purified TA in crystal form, we have chosen the continuous graph tube buffer and crystallizer with agitated thin film evaporator. We choose DTB because it involves both evaporation and crystallization. Agitated thin film is operated under reduced pressure, and DTB is suited for vacuum cooling and for processes having a moderate evaporation rate. So DTB is suited for vacuum cooling, so we can reduce the cost. And the advantages of using agitated thin film evaporator is short residence time in the heated zone. Second one is minimum batch mixing. Next, less product decomposition, which result in higher yield. And the last one is higher recovery. And the advantages of using DTB crystallizer is less problem with encrustation on the wall, as the heat is not withdrawn via the wall. Next, capable of producing light singular crystal. And the most important is the lower operating cost.
Next, I will talk about the description on how the chosen separation system works for the production of purified TA, including the operating conditions. So our separating system, there are two parts, which is evaporator and crystallizer. I will talk about the evaporator first. For the evaporator, we decided to use the agitated thin film evaporator. It consists of a jacket shell precision machine from inside and a rotor having blades that maintain a close clearance from the shell. A feed distributor at the entry point distributes the liquid in the thin film on the heated wall. The high-speed rotor further spreads and agitates the phlegm as it flows down. The heating medium will pass through the jacket to evaporate the volatile component in the feed. The vapor generated will flow counter-currently to the feed and get clear in entrainment separator before leaving the vapor nozzle. The concentrate products will then come up from the bottom of the evaporator. The process, the unit is shown in this picture. So for our process to produce PTA, the condition in the separation unit, which is the evaporator, will be set as 3080.142 kg per hour of feed at 2067 degrees Celsius, with the steam entering at 101.325 kPa. The steam temperature is 100 degrees Celsius. We choose our evaporation unit with the reference of the journal. For the agitated thin film evaporator, it can actually quickly separate the volatile component from the less volatile, and the separation is made under vacuum condition to maximize the temperature difference while maintaining the most favorable product temperature, as well as to maximize the volatile stripping and recovery. Our agitated thin film evaporator consists of two major assemblies, which is a heated body and a rotor. The evaporator unit is constructed with a carbon steel, which it can withstand the acid, which is the TA. Our evaporator also contains heating jackets, which can be designed for the steam of 101.325 kPa. And the rotors utilize conveying elements, which allows this unit to handle viscosities up to 200,000 MPa second.
Next, we move on to the crystallizer. For the crystallizer, we have chosen the draft tube and baffle type crystallizer. What is a draft tube and baffle type crystallizer? The draft and baffle type crystallizer is an elaborated mixed product removal design, which is suited for vacuum cooling and for processes having a moderate evaporation rate. So since almost heat makeup is required, the arrangement is compact and hence initial investment is minimized. It is capable of generating high purity products with a relatively low energy input. So we have found that both of the size and the quantity of the crystals are very important. So the DTB crystallizers are especially useful in multiple stage cooling crystallizer applications, where cooling of the feed solution in each stage limits the natural slurry density to a few percent. So this is the image of a crystallizer. Okay, for the description of the crystallizer, it is equipped with a stirrer so that the dimension of the crystal is uniform. Next, this is continuously flash vaporized by decreasing the pressure and temperature starting from 170 degrees and 114 psi with references from Meng Li, 2013. So along with the decreasing temperature, the saturated solubility coefficient is decreased. So that means the concentration of TA is increased according to Takebayashi. So then the TA is continuously crystallized out from the solution and the crystal particles started accreting. So there is no more 4-carboxyl benzaldehyde, 4-CBA, and p-methyl benzoic acid, PT acid, in the solution, which makes the TA solid separated from the solvent. So the remaining residual solvent can be separated by the methods of centrifugal separation, filtration, and dryness. So by the end of all these methods, we can obtain the final powdered PTA product.
So next I will talk about the strategy to maximize the production of purified TA in powder form. First, I will explain the strategy in terms of respective separator. First is I will talk about the evaporator. First, I will use the control rate evaporative cooling method. This is because the instantaneous flash evaporation of solvent may cause soft cooling and precipitate the dissolved impurity, which may contaminate the TA product, and this will affect the final production of purified TA in powder form. So to prevent the contaminating effect of such short cooling, the evaporative cooling should be controlled by evaporation against the
equilibrium bed pressure. For example, thawing of steam vapor and dissolves at the equilibrium pressure. Next is the evaporator should be operated at high pressure with low temperature. This is because foaming or falling of the product may occur during the vaporization. So high pressure or low temperature can reduce the vapor velocity in the tube, which can maximize the purified TA production. This is because when the total heat transfer coefficient decreases, the rise in the PTA decreases due to the pore convection. Number 3 will be material of evaporator should be made by steel. Its specific is carbon steel. This is because many solutions attack ferrous metal and contaminating by them if we're using the normal one. So the evaporator made of steel can minimize the corrosion and avoid the contamination. Scale depositions also should be avoided as some purified TA can deposit solid material on heating surface. So this may cause overall heat transfer coefficient decrease and corrode evaporator. As a result, decrease in solubility and the production of purified TA in the powder form. Next, I will talk about the crystallizer. According to the journal we read through, continuous crystallization and water addition method can maximize the production of purified TA in powder form. So, continuous crystallization of TA in the presence of more soluble contaminant, wherein water is injected into a large recycle loop for each crystallizer. And the continuous crystallization and addition of water make sure the dome operate at temperature of 191 degree to 149 degree, even below this range of temperature. So if the operator is operate at such temperature range, this can decreasing the proportion of originating dissolved TA.
So here is our sample calculation for the strategy to maximize the purified TA in powder form. So here is the schematic diagram we draw. As you can see, our fit is 3000 0280. This is based on the reaction part with the here is our fit calculation. We convert it to kg per hour and then times with our conversion rate, we get the fit for the evaporator. Then so here the assumption we get it from the journal is according to the meaning, the SF is 0.2 and gravity is at 267 degrees. So for the evaporation, we don't have boiling point innovation, so our vapor will be 0 and staying set at 100 degrees and 101 kPa. And our desired solute composition in the liquid will be 0.5. So here is our calculation. We calculate our solute balance first by using this formula, and we get our L equals to 1232.22 kg per hour. And we go to the overall balance using this formula, and we get the P vapor is 1848 kg per hour. So the next step is the heat balance. We start our L and P into the equation, this one, and also calculate for this, we also start the value into this, we get our S value. So after the evaporation, the feed of come from evaporator goes to the crystallizer. So the feed will be 1232.22 kg per hour, and the composition of solute is 0.5 in our feed. So the composition of water also 0.5. And after the assumption, we assume there is no evaporation in our vapor stream, so our W stream is equals to 0. According to the journal mainly we read through, the operating condition for the crystallizer is set as 114 psi and 170 degrees Celsius. And this is the information that we get from the website. Molecular weight of PTA is 166.13 grams per mole, and molecular weight of water is normally 18.015 grams per mole. The solubility is we get it from one of the journal that 0.715 grams PA per 100 water is when it is at 170 degrees Celsius. So this is our calculation. We first have to calculate the composition for the each stream first, and then we can do the water balance using this formula. We start the value we get, and we can get our C is equal to this 6,286.84 minus 10.1325, and this is our equation 1. Next we go to the solute balance using this formula, and we also do our calculation. We get until here, this is our equation 2. Then we start our equation 1 into equation 2. We can get our S is equal to 553.45 kg per hour, and C is 679.09 kg per hour. And for the calculation above, we can know that almost 55% of the fish is is what we expect